Thanks for the introduction, and it's really great to be here. Thanks for the invitation to speak, and thanks Web for organizing this wonderful workshop. And as a faculty member in a bioengineering department, which is amazing, just to clarify, but you often have to give talk to quote-unquote interdisciplinary audience, where you are quite reserved in terms of putting equations in the slides. But I was pretty happy when making these slides, because I thought for this audience, I could just throw in a bunch of equations in some of the slides and not feel too guilty about it. Hopefully I'm right. So for the modality that this talk will be focused on today, it's a little bit unique in the realm of MRI-based imaging. And when we think about MRI, these are probably some of the images will come to mind first. You see multiple beautiful contrasts allow you to look at the tissue, the same structure with different perspective. And then you can also use this signal from the water molecule in your body to derive some biophysical parameters, allow us to characterize the tissue differently, achieving this quantitative MRI capability, which is quite exciting. In the meantime, if you zoom in into individual voxel, in here you see a tremendous level of molecular cellular complexity, which cannot simply be captured or explained just by a few number of pixel values. And MR spectroscopy imaging, so-called MRSI, is one of the tools that allow us to resolve this molecular level complexity at the tissue level by combining the imaging encoding of MRI and the chemical specificity of NMR spectroscopy. We can obtain each voxel spectral look like this, with different peaks coming from different molecules in the body. For example, in the brain here, you can detect signal from hydrogen atoms, like hydrogen nucleus, such as most people do. In MRI, you can detect signal from other nucleus, such as 31P, carbon-13, potentially providing quite a comprehensive characterization of biochemical profile at the tissue level. And oftentimes, if you use two of these nuclei, it is actually label-free, so you don't need to inject any contrast agent into the body. This unique molecular imaging capability was promised to have many potential applications. For example, in the brain, you can have basic neuroscience studies studying neurotransmission system, as well as many neurological applications, as some of the examples listed here. Sometimes having a one-dimensional spectrum for each voxel may not be enough, because if you look at this beautiful looking spectrum, there are peaks coming from different molecules that they overlap with each other, making separating them actually quite challenging. So it's actually hard to achieve the molecular specificity that was promised by in vivo spectroscopy. And you can add additional dimension to this imaging problem by acquiring multiple spectrum for each voxel and do the things that you typically do to the water molecule. For example, you can add relaxation encoding, you can add diffusion encoding. Why do you want to do that? Because this one of the examples is that this allows you to better separate signal coming from different molecules. Because if you look at this kind of relaxation encoded spectroscopy, they don't just simply follow a decay, such as what you see in the T2 decay in the T2 weighted MRI. For example, different signal coming from different molecules actually accumulate different phases, allow you to better separate them to achieve better molecular specificity. You can also add diffusion encoding. You can derive molecule-specific biophysical parameters such as diffusion coefficient for different molecules. Why do you care about this, given that there's already a powerful imaging tool called diffusion MRI? Because diffusion MRI only measures the signal from the water molecule in each voxel. And water molecules are everywhere, intracellular, extracellular, in different cell types. But if you look at each voxel, there are different compositions of the cellular type, tissue compartments, and most of these metabolites are predominantly intracellular. And some of them are enriched in specific cell type. So if you can do this well, potentially you can provide a new dimension of information, allow you to probe tissue compartment specific or cell type specific microstructural information in vivo. Of course, this is easier said than done, because there are a couple of fundamental challenges associated with this kind of imaging modality. Number one, as you have seen, is a higher dimensional imaging problem because you're adding additional spectral dimension to each voxels. And even worse, the signal of interest here from these molecules typically have 3 to 4 order of magnitude of abundance lower than the water molecule typically used in MRI. So it's intrinsically a very SNR limited modality. And even if you get a nice looking spectrum like this, it's also a long-standing challenge. How do you actually accurately separate this signal coming from different molecules to achieve the molecular specificity that was promised for this kind of modality? So typically, the state of typical clinical use MRSI exam constrained to centimeter level resolution takes a long time to acquire this kind of data. And mathematically, you can define this imaging problem as recovering this multi-dimensional spatial function, as illustrated by this figure here, from this KT space data, multi-dimensional KT space data with very low SNRs. This T dimension is not typically denoting the work clock time that we are talking about in dynamic imaging, but the spin clock is reflecting the free induction decay of the molecular signal. So for the past 10 years also, starting as when I was a graduate student in Ji-Pei Liang's lab, we have been trying to develop a new approach that allows us to integrate physics-based low-dimensional modeling, fast spin physics-based fast acquisition, as well as ML AI power computational algorithm to address some of these fundamental challenges from an end-to-end fashion. One of the driving approaches that we have been using is this partial separability model and this SPICE imaging framework, in which basically we recognize that the signal coming from each voxel come from a small number of molecules that you can actually detect in vivo. Each one of them have a well-defined spectral signatures that are controlled by a small number of molecular spectral parameters. So the mathematical consequence of this is that if you can find the right distribution of the parameters, then the signal each voxel can be well approximated by a combination of a small number of basis functions, spectral basis functions, or temporal basis functions. If you can predetermine these basis functions, then you can redefine this high-dimensional imaging problem into the recovery of a small set of low-dimensional coefficients, significantly reducing the dimensionality of this imaging problem, making better trade-off between spatial resolution, speed, SNR, and molecular specificity possible. And we have also extended this straightforward multi-dimensional subspace imaging model to capture the multi-dimensional MRSI signal. In this case, you can extend your basis to capture multi-dimensional spectral variation, as well as inducing this component-specific molecular representation, assuming each one of the molecular components that you are interested in reside on their own low-dimensional subspaces. And this can be defined in a more task-specific fashion. For example, if you are interested in separating this major metabolite signal that everybody does, as well as a couple of neurotransmitter components, for example, the signal from a GABA molecule, the primary inhibitory neurotransmitter, or the glutamine representing the excitatory neurotransmitter, you can define your model into these three components, with one capturing the major metabolite and two others capturing the GABA and glutamate signal specifically. Now, one of the key issues here is how do you determine this low-dimensional subspace so you can do this effectively. As Dan mentioned in his talk, contexts are very important and helpful in designing an imaging experiment. In this case, we actually have decades of context and prior information about the signal that we are trying to detect and quantify. For example, from years of chemistry and biochemical studies, we know that in the ideal situation, what the spectrum from each of those molecules trying to detect should look like using molecular structure and quantum mechanical simulation. They can also draw data from the prior experiment, as well as the literature data, as well as some of your own data, to construct distribution about many of these spectral parameters that you can use to define a realistic looking spectrum. Then you can feed this combination of information into well-defined biophysical model, one of those listed here, to simulate as many physiologically meaningful, realistic looking spectrum that you can generate. And from there, you can define and learn low-dimensional structures and use them in the imaging experiment. Once you can learn this low-dimensional subspace, you can actually define a relatively straightforward explicit rank constraint reconstruction to recover your high-dimensional spatial function. But in the meantime, this kind of model also allows us to rethink about how we can actually acquire the high-resolution MRSI data. A couple of examples here. The first being a strategy that we developed for SNR-efficient multi-echo MRSI acquisition, allow us to achieve multi-T spectroscopy acquisition. In this case, we integrate fast spectral encoding with a little bit of spatial temporal sampling, allow us to generate high-resolution MRSI data in a rapid fashion. And we will also interleave some of the water acquisition into the same scan. So you can obtain some auxiliary anatomical as well as some of the information you can use for helping processing this data. in the same scan without requiring additional scans. Here's another example. We can combine diffusion encoding and fast MRI acquisition. In this case, allow us to achieve fast, robust, high-resolution diffusion MRSI to enable multi-metabolite diffusion parameter mapping in clinical feasible time. So if you do a few things right and combining together, this is one of the capability that you can achieve. In this case, we are achieving in the single scan simultaneously mapping of a number of metabolites in the brain as well as a couple of neurotransmitter and their relaxation parameters in clinical feasible time and millimeter resolution. And you can combine diffusion encoding with MRSI, achieving this high resolution multi-metabolite diffusion coefficient mapping, achieving more than order of magnitude higher resolution than any of the method out there in terms of diffusion weighted spectroscopy in clinically relevant time. So this work has been selected as a finalist for this year's ISMRM Young Investigator Award. So if any of you are going to ISMRM, I really encourage you to check it out. Happy to discuss this as well. So very exciting results. So the question here is low dimensional linear subspace always sufficient? The answer is it depends. In this case, I'm simulating a collection of spectrum coming from this molecule called glutamate with varying degrees of spectral variation. As you can see, as you increase the spectral degree of variation, this collection ensemble of glutamate spectrum showing a slower down of singular value decay, indicating that you will have to use a higher order of subspace or higher order low rank model to recover your functional interest, kind of counter-effective in terms of the low dimensional, the purpose of low dimensional modeling. Here's a further concrete example showing that if you have a more narrow spectral distribution, one of the unseen spectrum here, you can approximate it to a very high degree of accuracy. But when you have a larger variation in terms of spectral parameters, the representation accuracy starts to degrade substantially. So the question here is, can we go beyond the linear subspace model by leveraging some of the recent advancement in deep representation learning? Here's one of our attempts by leveraging deep neural network, combining this convolutional autoencoder type of architecture, allow us to learn an effective low-dimensional representation of this high-dimensional, multi-dimensional spectrum, of course, using complex value unit because the phase are really, really crucial here. And here's some example showing that in different cases, the learned and linear low dimensional representation can achieve a better efficiency in terms of dimensionality reduction, achieving higher representation accuracy at the same model order compared to the linear low dimensional subspace. Now, how do we incorporate this into our reconstruction exercise? Here is one example. We hope to combine the well-defined forward physics-based spatial spectral encoding model and our learned low-dimensional representation. In this case, combine this data consistency constraint that you have been seeing in some of the previous talk. But in this particular case, you need to incorporate some forward model considering the uniqueness of the MRSI data. For example, this operator incorporating the field inhomogeneity effect. And this constraint basically enforces that the signal of interest reside on or near this low-dimensional model you're trying to learn. And you can solve this problem using this ADMM-based iterative algorithm. The first step is actually pretty straightforward, just a standard regularized least square problem. The second problem is a little bit more interesting. You can basically enforce this low-dimensional representation, but if you directly solve this problem, you need to do backpropagation through the entire representation network. So instead of doing that, we jointly learn a projection network and the representation network allow us to just solve this problem by doing a simple one step of forward propagation of the data through this projection operator. And the other steps are just part of the atypical ADM algorithm. Here are some simulation results in which we actually show that using this learned and linear low dimensional representation, you can achieve better reconstruction compared to other of the standard methods. And in this case, it simulated the 31P MRSI, which is known to have larger spectral variation due to pH changes in vivo. And here's another in vivo proton MRSI data. As you can see here, again, using the learned and linear representation, you can achieve a better reconstruction, so in better contrast for some of the molecule here, as well as better spectral quality as indicated by this arrow here. Now, this is all great, but after all, these are spectral constraints, learning from spectral data only. So we were thinking, can we push a little bit further by combining these learned low-dimensional spectral models, as well as some of the other more advanced spatial temporal or spatial spectral prior that we could learn using some of the more advanced deep learning strategies. So the unique challenge for this case is that compared to the other MR, deep learning-based MR reconstruction, it's really hard to obtain either high resolution or high SNR MRSI data. It's just very difficult. And those typically needed for either self-supervised or supervised learning strategy. For example, for self-supervised data splitting strategy, you still will prefer to have higher SNR data. And in the meantime, you do need a strategy to allow you to effectively account for this multidimensional correlation, spatial, temporal, spectral, and parameter dimension in your data. So the typical approach to solve this problem, as you can probably imagine, is through simulation. So as you see earlier, we can simulate realistic looking spectrum for the spectral prior. There have also been efforts trying to simulate spatial pattern of different metabolites. But as you can see, it's very difficult for the simulation to capture all the realistically looking metabolite distribution, especially for all the metabolite and their associated spectral parameters. So we draw inspiration from the recent advance in self-supervised denoising developed in the computer vision realm, and think about if there are ways to train a denoiser using noise MRSI data only. So one of the examples shown here is that we leverage the noise void concept and build this network to do spatial temporal interpolation. So specifically, we can break down this high-dimensional data into spatial temporal patches and do some random masking and train this interpolator network and then later use as a denoiser. And one of the unique features here is that you need to consider the spatial temporal characteristics in the MRSI data. For example, in this case, we decided to do the interpolation locally and the time interpolation globally because the FID signal evolution follow a globally well-defined biophysical model as we shown earlier. And we can also extend this to multidimensional MRSI data. In this case, we introduce some of the recurrent features to allow us to further exploit the spatial, spectral, as well as the additional dimension, correlation in the additional dimension. In this case, there's a model TE. We can also introduce other type of parameter dimension as well. So once we train this self-supervised denoiser, then we can figure out a way to incorporate it into regularized reconstruction formulation as been done by many of the work that established in the audience here. We can also combine it with a traditional spatial constraint, such as age-weighted constraint, and integrate it with our subspace, low-dimensional subspace model, with the V hat here indeed come from a pre-learned low-dimensional subspace. And using the idea from the plug-and-play ADMM, this problem can be decomposed into this iterative step among the three sub-problems. The orange block is very typical quadratic regularized rank constraint least square problems. And then the blue block is a little bit interesting because updating this auxiliary variable is basically equivalent to applying the pre-trained denoiser. We actually apply a low-dimensional subspace projection here to improve not only just the performance, but as well as the convergence as shown in this next slides. So it turns out that you can map this plug-and-play ADMM algorithm into a fixed point iteration. And one of the key criteria for this fixed point iteration to converge is the contraction factor for this operator T here needs to be smaller than 1. But it's very hard to analytically compute what the construction factor is for this deep network-based prior. I'm happy to discuss if you have any ideas. But what we did is we did a numerical validation, and we compute this construction factor for our operator through different number of iterations. As you shown here, without the subspace projection, the construction factor gradually increased and get on top of 1, so giving us unstable performance as we progress through the iteration. But introducing the subspace projection actually helped us to promote the convergence, actually achieve better performance in this case. And here are some results. First of all, simulation. We took a lot of time to acquire one set of quote-unquote ground truth data with 6 averages in this 3D MRSI data, and use that and do some pre-processing to it to create a quote-unquote gold standard. And then we pre-train our self-supervised denoiser using single average and also do reconstruction from single averages. As you can see, we achieve lower reconstruction error as indicated by this Y ladder here, mean square error compared to the some of the state-of-the-art subspace-based reconstruction with some standard total variation regularization. You can also see that we achieve smaller spectral quality. And something also very interesting here is that if you just directly apply the denoiser to the data, you can actually improve the SNR, right, to a great extent. But incorporating that in a iterative reconstruction formalism, combining with other constraints, including subspace model, you can achieve significantly better results. And one thing very interesting here, you can actually, this is a typical phenomenon that many people observe, is that if you do this kind of self-supervised denoiser training, if you train it for a long time, the errors start to increase because they start to overfit the data. The noise overfit the noise. But then by introducing it into this reconstruction formula and using the same denoiser, you start to get a more stabilized reconstruction reconstruction results. So here are in vivo results from a healthy volunteer. As you can see that, again, this proposed method allows us to recover a more realistic looking spatial pattern and tissue contrast for different metabolites compared to the subspace-based reconstruction. And here's a result from a patient. In this case, this patient suffered from traumatic brain injury and later developed epilepsy. You can see a couple of the lesions here. And you can see that by combining subspace model with this self-supervised learned denoiser, you can better recover the unique metabolite, the spatial pattern for different metabolites. So this is done via our collaboration with our local clinical partners. In this case, you can actually acquire this data in about 8 minutes time. And here's a further look at one of these data, which I consider quite interesting. So why do we care about this? We further look at the map of different metabolites. For example, this major metabolite NAA, which everybody does, and then 2 of this neurotransmitter. In this particular epilepsy patient, you can see that some of the lesions, one of the lesions saw a more significant reduction in terms of GABA compared to glutamate. So which indicate a imbalance, potential imbalance in excitatory inhibitory neurotransmission. And why do we care about this? Because for about 20% of TBI patients will develop epilepsy 5 years after the initial injury. And it's very hard to predict which one has a higher likelihood of developing seizure. All you have right now is a population-based statistics. What we hope is that by leveraging this unique biochemical signature of the tissue and integrating it with other anatomical functional measure, perhaps we can offer a way to better predict the risk of seizure for individual patient. Then you can probably deploy a more proactive treatment strategy, such as giving early anti-seizure medication to reduce the risk of developing seizure and later epilepsy. Here's another patient data. The earlier data were not as good looking as this one, but you can still see that one of the lesion compared to the other shows different pattern in terms of reduction and excitatory and inhibitory neurotransmitter. And with that, I would like to acknowledge the students, outstanding student in my group who did most of the work. I did contribute to some degree, and the funding resources. And just to know that some of the directions that we are pursuing beyond just MRI, MR spectroscopy allow us to better probe the biochemical level information in the brain. And finally, I would like to conclude with this slide. This is one of the plenary sessions held in 2014 at RSMRM. The title is called Promising MRI Techniques That Have Yet to Leave Home, Challenges to Widespread Clinical Adoption. And MR spectroscopy is listed one of them. So we are about 1 decade later. Whether MRSI have left home yet, I don't know. I think the decision is up to the community. But for the student and trainee in this audience, why would you work on something that already left home, right? So something to think about. And it's really a pleasure to talk about MR spectroscopy at this particular campus because so many pioneers in this field that I highly, really, really respect. Thanks, and I'm happy to take any questions.
Yeah, Dr. Fan, very nice talk. I'm not actually doing MIS, but I'm doing SAS. So like one topic, I'm like ahead of that. Right. But I also have some experience dealing with MRS data, and like we're actually doing like other organs, and we find basic set is also important in the traditional LC model analysis. And from the data you just show, like even in patients, your methods work very well with them. And I remember you also mentioned the prior in your like kind of regularization terms. And I wonder if you could provide like more details about how you get the prior for the patients.
Oh, that's a good question. If I understand it correctly, you're asking about how do we obtain effective prior for the patient data? Is that only from healthy volunteers? Is that correct?
Yeah, because like you have shown lots of healthy brain images of MRI, and I wonder if you go to like a brain tumor or go to tumors in the body, would that be a little different?
Yeah, so that's a good question. So the fundamental idea of this data reside in a low-dimensional subspace will not change between population, but the exact subspace probably will change. So it is important to combine this kind of simulation-based and data adaptive adaptation. There are multiple prior mentioned here, right? So one of the driving model is a subspace model here. So there's a multi-pronged approach to address the issue that you are referring to. For example, in the simulation, you can also build in the context about that disease and then simulating spectral distributions, parameter distributions that is more relevant to that particular population. And also you can simulate a larger degree of variation. That's why we want to use a more powerful like linear representation instead of linear low-dimensional subspace. In the meantime, I do want to emphasize the utility. You also want to have some population-specific data, which is indeed what we were doing here. So you want to acquire some population-specific data, and you want to adapt your pre-learned subspace to the variation to individual experiment. So it's a data-dependent adaptation that we do in the practical experiment. I didn't dive into the nitty-gritty details here, but it is important to account for those. And for example, for the self-supervised denoising prior, it was actually learned from the data itself. So you can actually learn from individual patient. So that is indeed a little bit, I guess, less sensitive to the population bias. That if you only train a denoiser using healthy data, then you probably can introduce substantial bias into your particular population, such as PTE, tumor, stroke, etc.
Yeah, sounds good. Thank you so much.
Great, thanks.
Thank you. I think there was a highly related question asked online. If the person who asked that doesn't think it was answered, please clarify your question. In the meantime,
yeah, thanks for a really good talk, and I indeed loved the way you used plug-and-play priors in self-supervised way for reconstruction. I had a question about actually a higher-level question in some sense. So the real data is super messy, and it looks like MRSI is particularly going to be really messy.
Exactly.
How consistently can you recover same signatures or spectral signatures from scan to scan? Is this an issue, or it's usually a stable, especially with your powerful algorithms?
Yeah, it's a big issue. So of course, if just these tools are enough, it wouldn't take 10 years to get to these results, right? So you are absolutely right. The data are very messy. So there are a few steps that are ignored here, but absolutely important. Unfortunately, you can't really publish a paper on those. For example, there are pre-processing steps to correct for system-related instabilities, magnetic field drift. There are significant investment into how you can remove the quote-unquote nuisance water lipid signals. They are what you use in MRI, but now they are nuisance. They are contaminations, kind of preventing you from effective reconstructing metabolite signals. There are a few inhomogeneity correction steps. There are a number of steps that I didn't touch on here because time and space constraint, but you are absolutely right. So it's really an end-to-end solution, as you can see. Only reconstruction here would not be enough. So it's really starting from the acquisition design and pre-processing, reconstruction, quantification, in end-to-end fashion to allow us to achieve this type of performance. And finally, yeah, I think I'm not showing here, but if you go to our paper, reviewer typically ask for how reproducible these results are. So we have some test-retest study to show that this is indeed at least more reproducible than some of the standard methods.
Thank you.
Great.
So if there are no more questions, let's thank the speaker once more.
Thank you.